In this lecture, we're going to continue with the topic on wave transformations. Next, we look at wave run-up, which is defined as the maximum vertical elevation which the water rises on the beach or a structure using the residual energy after wave breaking. So for example, over here, we have the still water line, and the wave is actually able to run up the shore up to this point. So that will be the total run up measured from the still water line. If this is a structure with a sloped surface, then the same approach to solve the problem is also applicable. Wave run-up is important to be considered so that in the design of coastal structure, we will determine a suitable beach setback line or platform elevation to avoid wave overtopping. For example, if we know that the wave has the capability to run up to this position, then we may not want to build our building or our beachside restaurant over here. And if we build any structure, we will want to make sure that our structure has a crown level which is higher than the run-up point, so that the water doesn't go over the structure to flood the inside or the land side of the structure. Now, wave run-up is dependent on the toe depth. The toe depth is defined as the water depth measured at the point where the beach slope changes direction. So these are the major factors that affect the run-up magnitude, which includes the slope surface roughness, the slope profile, the wave height, the wave period, and also the toe depth. Here we show an example of a chart used to estimate the run-up, and again, these charts are produced from observations around the world. This is a dimensionless run-up on smooth impermeable slope. So if the slope is something else, for example, it is a permeable slope, it is not a smooth slope, then we have a different set of plot. So for the sake of the discussion, we only show one plot here. This plot is taken from the Shore Protection Manual, and if you go there, you will be able to find many other similar plots for different types of surfaces. The updated version of the Shore Protection Manual is known as the Coastal Engineering Manual. Both are published by the USACE. They are very popular and is commonly used by the coastal engineers for all these different analysis and design. So for this particular chart, it is applicable for ds over h naught prime between 1 to 3 only. ds is the toe depth, h naught prime is again the unreflected deep water wave height. So again, you notice that this chart is very limited, is only for this type of surface and also only for this range of ds over h naught prime. So the other charts are available in the complete manual. The assumption is monochromatic wave approaching this smooth planar impermeable slope, whereby the slope is given by m. If the slope is m, then cotangent alpha, alpha being the angle of the beach slope, is 1 over m. You may want to understand this properly. All right. So the procedure of solving for the run-up here is, first and foremost, we need the value of ds over h naught prime, so that we choose the correct plot. After that, we want to calculate the h naught prime over gt squared, which is the value here, so that we choose the correct curve to use. We need to know cotangent alpha, which basically is 1 over m, so it represents the beach slope. So we choose the value here. Now once we find the value here and we know which curve to read, we read across to get R over H naught prime, and based on that we will be able to calculate R, capital letter R, which is the theoretical run-up, and after that we will multiply with the correction factor K and the small letter r to obtain the actual wave run-up. Check this out and make sure you understand the relationship between M tangent alpha, cotangent alpha. This is actually the original plot of wave run-up on smooth impermeable slope with ds over h naught prime equals to 2.0. This one is wave run-up on smooth impermeable slope when ds over h naught prime is larger than or equals to 3. This figure is for us to obtain the correction factor K for run-up scale effect. The vertical axis here is the tangent theta, or basically the slope of the pitch, and whereas here is cotangent theta, which basically is the inverse. You notice that it is 0.5 or 1 over 2, and here become 2 over 1, so it's the inverse. Now we have two curves here. This first curve is measured from large scale model test, whereby the wave height range from 1.5 to 4.5 feet. So these are experimental data. So if our problem falls within this scale, this magnitude of wave, then we can use this curve to obtain the correction factor. So by knowing our tangent theta or the pitch slope, we choose the curve, we read the K value. However, if our problem is a much larger problem with a wave height between 4 feet up to 12 feet, so this is a postulated curve. That means it is derived based on the actual measurement in scale model. So if we have larger scale problem like this, then we may want to choose this curve to apply the correction factor. So you notice that for the same pitch slope, for larger scale problem, our correction factor is also a larger value. Another correction that we will adopt is the value of R for various slope characteristics. So these are the various slope type, how they are being placed. For example, blocks which are being properly placed, or quarry stone which is randomly placed, then the R value are suggested as given in the table. So we will choose the appropriate value for the estimation of the actual run-up. This is a more simplified run-up factor R, depending on the different surface type on the slope. So as engineers, we will need to choose carefully. Usually a more conservative choice may be made, and as mentioned earlier on, when we design a coastal structure, we may want to make sure that the crown level is higher than the maximum run-up, so that the seawater doesn't overflow or overtop to the land side. Let's try this example we will discuss in our online class.